This particular session is a deep dive into the descriptor tables. So, what we saw earlier was about the segment descriptors. Now, we will move to the descriptor tables. So, there are 3 descriptor tables: the global descriptor table GDT, the interrupt descriptor table IDT, and the local descriptor table LDT. The global descriptor table is by default necessary. It maintains a list of most segments. It may contain certain special system descriptors as we have seen, like the TSS, and always the first descriptor is a null descriptor. I can't use it for anything. The interrupt descriptor table maintains a list of interrupt service routine as descriptors. We have already seen that. The local descriptor table, it extends the, it is optional, but today many of the operating system gives it. It extends the range of GDT, right? Something more than GDT I can store, and it is allocated to each task when multitasking is enabled. So, every task has its own LDT, and again the first descriptor in the LDT is a null descriptor. We can't store any value in the first descriptor in LDT. We are storing some value in the first descriptor of IDT because that is divided by 0, but here we can't store any value in the first descriptor of a LDT, be it be it whether it is a LDT or a GDT. I can't store anything in the first descriptor. Okay. So, where are these tables stored? They are actually stored in the memory, and the starting address of this is stored in GDTR, LDTR and IDTR for the GDT, LDT and IDT respectively. Now, what is stored in GDTR? We have not seen that so far. In the GDTR and IDTR, we store 48 bits in length. The first 16 bits, least significant 16 bits, will store the size of the table, and the remaining will store storing a 32-bit address pointing to the base of the table. Okay. So, I have, so in the GDTR essentially has totally 48 bits. 32 bits will tell where the table starts, 16 bits will tell me what is the size of this, right. So, 16 bits means what? 2 power 16, I have 64 kilobytes, but each thing is 8 byte. So, now you calculate what will happen. With the 16 bits, how much I can go? 64 kilobyte. Each is 8 bytes. So, how many segments can I store? 8 kilobytes. Hmm? 16 bit is the limit. So, if 16 bit is the limit, that means I can go to 64 kilobyte. Each selector is 8 bytes. So, this will be how much? 8 kilobytes, correct? Yes or no? So, 8 kilobytes, 8 kilobyte minus 1 segment descriptors I can store. It is not 255. Okay. Only for interrupt it is 255, but for GDT and LDT we can go up to 8. Right. We can go and adjust this 16 bit. So, I need not say every time it should be by default 16 bits. So, I can go and make it say I will only store 5 descriptors or 10, I can make it even 40, 10, 20. Right. It need not be occupying the entire 8 KB of, you are getting this. The limit field is what you set. So, if you want to create an LDT of size 10, you go and make that limit field as what? 80, because you need 10 descriptors. So, the limit field you can set on your own, but then you have to be very careful in setting the limit bit, so that exactly that much is. Okay. So, what is the important thing about this LDT, this limit field in both GDTR and IDTR? if I start accessing something more than that limit, then there will be a general protection fault, and that is very, very important for us from a security perspective, right. I can't go and try and access something beyond this limit, right. Otherwise I know where the LDT is stored, so I can look at some offset, right. So I have a 8 KB thing, so I can, if I can get some location very close to that and put my own entry there, I am gone, right. So I fix the limit. When I create an LDT for you, I store what is the base and I also fix the limit, so that if anybody starts accessing beyond that limit, then what will happen? There will be a fault, right. So when I give an offset, even for your move instruction, move ds comma some offset, that offset is checked with the corresponding LDT or GDT limit and if it exceeds that limit, there itself one general protection fault comes. You understand this? And that is very, very crucial. So LGDT, we are slowly going to the real tough part of this course. The LGDT and the LIDT. What is LGDT? Which is the instruction that will load into the GDT. What is LIDT? Load into the IDTR. They will point to a memory location which is 48 bytes in length. So you go there to that memory location and you find 48 bytes. The first 16 bytes load it as limit, the remaining 32 bytes load it as the base. You understand this? But in LLDT, what you do? It will point LLDT some selector. So it is a 16-bit selector pointing to an entry in the GDT, right? And in the GDT, there will be a local descriptor table descriptor, right, and that will point to a start address of the local descriptor and also thing, right. So LLDT alone will point to a selector in the GDT. That selector in turn will give you a start address and the it will point to a selector, that selector will give you a start address and the limit. In the case of GDT and IDT, you point to a memory location which is 48 bits in length, and there you will have what? First 16 bits will be loaded as limit and the remaining 32 bits as. So that is how this works. You got this, right? So now we will go into lot of this privilege checking things. Okay, we will be reiterating several things again and again so that we have a good clarity. Okay. So out of several segments described in your GDT and LDT, which of the segments that are currently being used are pointed to by the 16-bit CS, DS, CS, FS, GS and SS. So in your GDT and LDT, I could have n number of descriptors. I could have as much as that limit by 8. Right? I have a limit that divided by 8 will give me the number of descriptors I should have. But I could have more than 10 or 20 descriptors. As a program, at any point of time, I will be using one of those descriptors for code and some of those descriptors for data and one of those descriptors for stack, right. So there will be one, so I could have 10 code segments inside that LED. I can go between one code segment to another. One of those code segment will be used currently because your CS will point to exactly one code segment. One of those segments will be used for stack because SS points to one of those stack segment. Then for the data, I can use any one of ES, FS, GS and DS. Okay. Now since descriptors are at 8 byte boundaries, the 16 bit selectors store the first most significant 13 bits to point to the corresponding descriptor, right. Since it is 8 byte boundary, the last 3 bits are anyway 0, so the first 8 bits are stored. The bit 2, right, out of the 8 bits, the 3 bits, the bit 2 is the T1 bit, which when it is 0, it implies the selector is pointing to a descriptor in GDT. When it is 1, it implies the selector is pointing to a descriptor in LDT. And then there are 2 bits other than this, which is 0, 1, and they are called RPL. This is called request privilege level bits, which we will discuss about this in a greater detail in when we go into task switching, etc. Right? Okay. Now there are 2 privilege levels for a when I am trying to see, there is a descriptor privilege level which is stored in the descriptor, and there is in the selector there is also a privilege level which I am calling as request privilege level. You are getting this? There is a descriptor privilege level which is stored in the descriptor, and I am trying to access the descriptor. I am using a selector to access the descriptor. The selector also can have a privilege level, it is called a request privilege level. So we will not bother about RPL today, but tomorrow we will take it up. It is very interesting to note how RPL can be used. So let us go and do one more deep dive, again because we have talked lot of things in bits and pieces. So let us take one more deep dive and find out how we go about loading segment selectors into segment registers. Okay. So we will go into these details now. So these are all the rules that we would like to follow when we are loading a segment selector into a segment register. Okay. Whenever segment registers are loaded, how do you load a segment register? You do move ds comma something, move ss, es, fs, gs. For cs alone you use a jump or a call. Okay. Whenever a segment selector is to be loaded into a segment register, there are lot of checks that are happening, and these checks are very, very important from a security perspective. So we will again spend some time now to again reiterate on these important things. Okay. So I will read out these rules and explain these rules. Whenever segment registers are loaded, the following rules are checked by the processor, that is by the architecture, and if violated, an exception is raised, thus giving high degree of memory protection. Once an exception is raised, your control again goes back to the interrupt service routine and hence the operating system. Okay. So what is the rule 1? The index field of the selector should be within limits of the GDT/LDT that we are trying to access. Otherwise you raise a general protection fault, which is some fault number 30 we have seen. Right. So where do I set the limit for this? When I do my LIDT or when I do my LGDT or LLDT, I set the limit that so many descriptors alone can be there. If I exceed that, then there is a general protection fault. Rule 2, when I am loading a selector into DS, ES, FS or GS that points to a non-readable segment, it results in an exception, right. So when I am loading, what are non-readable segments? Execute only segments. Okay. So I have different types of segments here. I will cover that in the I think I have done something in the previous things. Yeah. So as you see here, suppose I have 100. This is a code execute only segment. Okay. 110, it is a confirming code execute only segment. You getting this? So these segments, if I start loading it in SS, DS, ES, FS, GS, I can't even read, not even write. So if I haven't, I can't even read it, right? It's a only execute only segment. So I should not be in a position to even read it. Correct? So if I have an execute only segment, so this basically explains this. So when I am loading a selector into DS, ES, FS or GS that points to a non-readable segment, that immediately results in an exception. For loading into SS, the segment pointed to should be not only just readable, it should also be writable, right? Right? So it is not just non-readable. Non-readable is not just readable alone. It should be first readable and also writable. Otherwise, it will give you an exception. So please note that a lot of checks the architecture does before it allows you to start using a segment. And if you rigorously follow these rules, your operating system has to be secure. Correct? The main point why today there is vulnerability is many of the operating systems have forgotten these rules or not used these rules. Correct? You follow what I am trying to say? Right. Now the rule 4 is when I am loading into CS, the segment should be an executable type segment. There is executable read, non-conforming executable and non-conforming executable read, but it should be a executable segment. So if I write a data segment into CS, then automatically it will give you a fault. And then the privilege level check rules are to be described later. We will describe that in more detail, but already we know that if I am at a privilege level K, I can load only, my current privilege level is K, I can load only something greater than K. So all segment registers except CS may be loaded using move instruction, move DS comma something, or it can be using LDS, the load data segment, load ES, load FS, load GS, LSS. These are all some of the things that are present today. And the CS is loaded using a jump or a call. We have already described that in the previous notions, and now we will discuss that in a much more broader detail when we do the assignments. Okay. Now what is this local descriptor table? I said LGDT and LIDT. I told that it will LGDT some memory location. In that memory location what will be there? It will have the 48-bit address. Similarly LIDT. That 48-bit means 16-bit for limit and 32-bit for the base. But now we look at LLDT. LLDT will point to some selector inside the GDT. Right? What is that selector? That selector will have a 32-bit base as you see and a 20-bit limit with a present bit, and there is some bit pattern 0, 0, 0, 0, 0, 1, 0. This is how that 64-bit is organized. The 0, 0, 0, 0, 0, 1, 0 is nothing but the system bit and the type bits. So this is a system descriptor, unlike a user descriptor that we have seen in the past. This is a system descriptor and it has a type here, and that will be the type here. And then there is a present bit, and then some bits are hard coded to 0. So this is how a 64-bit descriptor in LDT of a LDT will. So what this will give you? It will give you a base address, plus it will give you a limit which is 20 bits. Okay, right? It will give you a base address which is where the LDT will start, and it will give you a limit which is 20 bits here. 20 bit means I can go up to 1 megabyte. 1 megabyte and each is 8 bytes. So 1 meg by 8 what? I could have 256 kilobytes of, right? 256k of 125 kilobyte, 125 kilo, 125 into 10 power 2 power 10 LDT entries. LDT interest, right. So, this is how LDT goes.